Look closely at a dividing cell, a sprawling root system, or a flock of starlings. Long before we had equations to describe them, nature was already multiplying, dividing, and expanding. Our ability to organize these complex observations started with a single repeatable behavior, the act of identifying individual units. 1, 2, 3, 4. This is the sequence of natural numbers. Early humans used this sequence to solve immediate problems. We needed to know how many sheep were in a herd, or how many sacks of grain were stored for winter. We carved notches into bone and pressed marks into clay to track distinct physical objects. Whether etched in ancient Mesopotamia or processed by a modern computer, natural numbers exist to answer two practical questions. How many are there? And what order are they in? Mathematicians formalized this habit of counting into a specific set. They denote it with a bold capital N, representing a collection containing the positive whole numbers starting with 1. But depending on the field of study, that exact starting point varies. The question is whether to include 0. In set theory, mathematicians define numbers by the sets they contain. Under a framework developed by John von Neumann, the sequence begins at 0, representing the empty set, a set containing nothing. You will find textbooks that start the natural numbers at 1, and others in computer science that start at 0. However, the arithmetic rules governing the numbers remain the same in both versions. Regardless of the starting point, this collection of units provides the essential structure for the more complex number systems that follow. In the late 19th century, mathematicians like Giuseppe Peano wrote axioms to codify exactly how these numbers operate. The core rule is the successor function, the logic that every natural number has one distinct immediate next number. Because you can always add 1 to any given value, the sequence has no ceiling. In this system, a largest natural number cannot exist. This contrasts with the physical world. The number of atoms in a star is immense, but it is finite. Natural numbers continue long after the physical universe runs out of material to count. Through these simple axioms of succession, counting transitions from a practical task into a theoretical engine capable of mapping infinity. To understand how this set functions, we must look at what it excludes. Take a negative value, like -3. A directional deficit, owing 3 apples, is not a count of objects and cannot exist within the natural set. The same applies to fractions and decimals, like 1/2 or 2.5. Natural numbers represent complete units. They cannot be split into parts. Because the set consists only of distinct, whole, forward-moving units, it guarantees that any two numbers can be compared. One is always definitively greater than, less than, or exactly equal to the other. By filtering out deficits and parts, the natural numbers provide a linear framework that allows us to rank and compare elements with total consistency. Within this boundary, the set is self-sustaining. Mathematicians call this property closure. Closure means that if you take any two natural numbers and add them together, the result is guaranteed to be another valid natural number. Multiplication obeys the same logic. Because multiplying is simply repeated addition, the product always stays within the boundaries of the set. As long as we stick to addition and multiplication, the natural numbers function as a self-contained system. However, the system encounters a crisis when we attempt to run it backward. Subtracting a larger natural number from a smaller one, like 3 minus 5, results in -2. This falls outside the set, breaking the system's rules. Division triggers a similar failure. Trying to divide 5 units into 2 equal groups forces the creation of fractions, which the natural numbers do not contain. These contradictions required mathematicians to expand the system, incorporating integers, rational numbers, and decimals to account for the complexity of the world. Even with these limitations, natural numbers generate complex internal structures. Evens, odds, factors, and multiples all emerge from the simple act of counting by 1. Hidden within this sequence are prime numbers, values divisible only by themselves and 1. They are the indivisible atoms of mathematics, scattered across the number line in patterns we are still decoding. These digits provide the starting point for arithmetic, algebra, and the binary logic that powers computing. If the sequence of natural numbers is truly infinite, then the potential for the systems we build on top of them is equally limitless.